Hi everyone, my name is Julien. It's my first time as a speaker at Geomob, so thanks for the opportunity. I work at Verso, which is a company that does optimization software. And when we work with location data, usually we handle vehicle routing problems, and we work on Vroom, which is the vehicle routing open source optimization machine. Basically, just starting off with a bit of context between routing and optimization. We have several routing engines available, even a very efficient open source routing engines, even for specific needs like we just saw. What does optimization brings on top of routing? Basically, instead of just going from A to B or designing a route with several legs with different waypoints, optimization just answers the question of ordering. How do you want to order your route if you are to visit? For example, in this screenshot, we have a set of points to visit around Paris. And of course, we want to minimize the overall travel cost. You probably already know this problem. It's the famous traveling salesman problem. And we want to come up with something like this, which will be efficient in terms of travel time and distance and so on. So this kind of problem arises not only for traveling salesmen, but every time you have a geolocated set of tasks. It could be deliveries, it could be services, home healthcare, it could be maintenance or whatever. So every time you have one or several people doing geolocated tasks and usually facing real life constraints to do that. So obviously there's not only one route to plan usually. Say we have the same kind of problem with capacity restrictions and we have a fleet of 4 vehicles. Basically we want to come up with something like this to make sure the capacity restrictions are met. And on top of ordering the stops, we are deciding how to allocate the subset of jobs to each route. And then there's virtually no limit to the real life constraints you can meet. We've all been waiting a long time for a parcel at home. So it's good if you can set delivery time windows, for example, so it stands for a vehicle routing problem with time windows. Sometimes we want to mix deliveries and picking up stuff in the same route and bringing it back to the depot, for example, that's VRP with backhaul. Sometimes you want to pick up stuff along a route and deliver it. And so a single route can go with several pickups, several deliveries, and mix those. So that's a pickup and delivery problem. By the way, this is not only limited to logistics, because a pickup can actually be a passenger getting in a car or a bus, and a delivery can be the same passenger reaching its destination. So actually it can be used in a mobility scenario where you have a fleet of vehicles that need to move people around. There are many different situations. If you're doing delivery, you usually have a depot, but sometimes you have several depots. You can have a fleet that is totally distributed, and you may want to optimize up to the last job in a route. So not taking into account getting back to the depot, stuff like this. So there's actually an endless list of constraints people face in real life problems. So basically, that's a tough problem. It's known in research to be very challenging. And the result of this is there's always a point where when the problem size increases in terms of number of locations, then the computing time will go completely wild. So obviously, if we want to have something practical and usable, we want to adjust the solving approach. I'm just mentioning this example. I love that example. William Cook is the authority on the TSP in the research world, and his team he actually came up with the optimal tool across nearly 50,000 pubs in the UK. So that's quite a lot of geobeers. But obviously, it's very impressive in terms of research, and they've been using cutting-edge techniques. But it actually took nearly 14 months and a lot of computing time. So it's not something that is directly usable in the field. So the idea behind the project, behind Vroom, is we want to meet some real life requirements. So obviously we want to have real life routing. We don't really care about optimal solutions. Obviously we want good solutions that are good enough or near optimal, but we don't want to spend an endless time getting them. So we want a good trade-off between the two. Low computing times are very important because they enable end users to have instant feedback. Like when you solve an optimization problem, sometimes the solution is not quite what you expect, and then you want to be able to change some constraints and move and pull some triggers to improve the solution. And being fast, having a low computing times is the only way to be able to really scale, to solve big problems in the 100 or 1,000 in terms of problem size. The features, the high level features is we try to maintain a very fast solving approach. We have a parallelized search, so we look up different solutions in parallel. And an interesting feature is that we offer what I call an exploration level parameter, which helps to provide different trade-offs. You can set it to a low exploration depth, then you get solution very fast. And you can also, if you're prepared to wait longer, you can increase the exploration, and it will take more time, but you may get a better solution. I like to present the optimization algorithm in the overall context in terms of layers. We have the data layer, so we rely on OpenStreetMap. Then there's the routing layer. So you have to just decide on what you want to use in terms of profile to find routes and travel times. And then the optimization layer runs on top of this. And the first thing we do when we have a problem to solve is we fire a matrix request to the routing engine. Here you see an OSRM logo. We have full integration with OSRM and OpenRoute service too. And you could actually switch the routing layer. For example, if you want to do optimization on top of a trail router or any other routing engine. A quick word on results. It's probably the most boring slide, but it's actually important in terms of measuring the performance, because computing results on benchmarks, on academic benchmarks, is the only way we have to assert that we have good solutions or not. So those are the reference benchmark for vehicle routing problem with time windows. Each of the instances have 100 jobs, and I'm reporting results with two different setups. I mentioned the exploration level, so the left column is the fastest solution you get, and the right column is the best we can provide. And you see that in both cases, computing times are very fast. We get solutions in around 50 milliseconds for the fastest approach, and not even half a second for the longest. And in around 20% of the situations, so that one instance out of 5, we actually do reach the optimal solution. And if you look at the second table, you can see that when we don't reach the optimal solution, we still get very good solutions. The median gap in the right column of 1.1 means that if the optimal cost is 100, in half of the solution, we get a cost that is between 100 and 101.1. So we are basically, the idea is we're really close to optimal, but we get solutions very fast. To detail, but just a way to show that the project actually started 4 years ago. It started as a proof of concept that we could have something very fast to solve a TSP. And then the development took up like 2 years ago. and we know have steady releases very often, and we try to keep that same efficiency in solving while adding new features along the way. That's it for the fun part, and know a bit about the profit, because obviously we need to fund our work on the project. I created a company called Verso with fellow researchers, and this company is actually driving the development and maintenance of the open source project. And we have a very typical business model for a company that develops an open source software. We have our own optimization endpoint. So we have an API, and people can subscribe, get an API key, and so we sell service, basically. In some situations, some of the users want to go with the open source stack, so they want to deploy the whole stack themselves on premises. In that case, we can provide support. Support also extends to problem modeling, because different use cases require different modeling, and people want to make sure they get the best out of the solving engine. So we can also provide support on how to best model the real life use cases we meet. And then one last point is that we do have clients or users funding new features. This is really interesting because it's a way for us to go forward and develop the open source tool, but once it's done, it's actually available to everyone, including our users. So it's a great way to mutualize the costs. And it does work pretty well since a few months now. I will end up with an example, a use case. Our API has been integrated into a transport management system developed by a French company called Telia. What you see in the screenshot is the usual dashboard on the left. So people have managed their fleet. They have their drivers, vehicles, the set of stops and constraints and so on. So they usually do everything, drag and dropping everything by hand. They also have a cartographic view. But what we actually do is we provide a simple building block that will automate most of the work. So they will be saving time by automating the optimization. The planning is much faster. Of course, they get the last word because they have a very specific expertise. But they gain time planning, and of course, we save travel times and kilometers on the spot. As you can see, they have pretty huge logistics players as clients, so that's nice use cases for us. And also, as a last takeaway from the talk, I'd like to say that none of this would be possible without OpenStreetMap data. As I said, we heavily rely on OpenStreetMap, not only the data, but the whole software ecosystem. We use several open source tools for routing and other stuff. So we're proud to contribute to this overall ecosystem by developing an open source solving engine. If you want to try it out, we have a demo. So head over to map.vroomproject.org. You can try it out, and you can check out the code on GitHub or follow us on Twitter. Thanks.
Thanks very much, Julien.
Thank you. Thank you, Julien. A question from Joanna. She asks whether your open source project is developed only by your company, or whether you've got a wider range of contributors from the community.
So far, it's mostly us. We started to see a couple of contributions. The most part, as I've mentioned, we have had financial contributions. So it's actually us doing the development and people helping us financially. But at the moment, it's mostly us. But actually, we are seeing more and more companies relying on our project. So I expect we will get more contributions in the future.
Okay. And I've got a question from Matthias. He says, have you worked with vendor-managed inventories where the central dispatcher simultaneously optimizes delivery quantities, creates orders, and determines route, i.e. fuel delivery? And if yes, what is your experience in terms of optimization, quality, and performance?
I'm not sure I get the difference between, like, say, a regular situation with a depot.
Yeah, maybe if I can add, so the major difference is that you actually, in that case, you don't have a fixed set of orders where you just need to solve the traveling salesman, but instead you're the one who actually decides which customer to deliver. And you may as well postpone a customer to the next week if the inventory at the customer side allows.
Yeah, sure. We do have this kind of situation where people delivering parcels, they have like a backlog of 3 days of deliveries, and the deliveries for this very day are mandatory, and then they try to fit in as much as possible for the rest. So in that case, they know in advance there will be unassigned jobs. So I think it kind of resemble what you mentioned, in that we provide solutions with unassigned jobs, but we to handle this, we have a notion of priority, so people can have a control on what jobs really need to be included in the solution and what jobs can be unassigned if not everything can be done.
Okay, I'm going to close the questions off there just because I want to keep us moving through the timetable. So I'm going to ask everybody to unmute themselves and to give